As our climates change, temperatures increase, and resources change, how will our food production change?
And what food will we be growing?
Do we have enough land to grow the needed grains, fruits, vegetables, legumes, and bioresources, plus other essential land use needs?
Hi and welcome. This is Brian. In the Climate and Sustainable Food Resources video series, we introduce several natural, technology, sustainability, and knowledge resources that are essential for sustainable and nutritious food production. We promote the use of modeling tools to project future food production scenarios. Much of the information presented is unique and customized. Virtual voice assistants help to describe various resources.
Linda here. Hi and welcome.
This is Richard. Welcome.
The first videos provide introductions to the major resources, followed by more detail in later videos. In 2010, 51% of all tomatoes were grown in the number 1 or blue area, and 78% were grown in the top 1 and 2 areas, as illustrated by the blue and darker green areas respectively.
Will we be able to profitably grow the same quantity of tomatoes in these two areas in the future? Where else could we produce this high level of production?
We begin with an overview of our natural resources, starting with solar radiation. The sun drives our climate systems, temperatures, precipitation, wind, and evapotranspiration, and it drives photosynthesis, the process where sunlight, water, and carbon dioxide are absorbed by plants to make glucose. Higher levels of solar radiation are received when the sun is higher in the sky, the days are longer, and the skies are clear. The levels are potentially reduced by air pollutants such as soot and ground level ozone. Net solar radiation received at the surface is one of the various parameters used to project crop yields. Changes in the carbon cycle and atmospheric carbon dioxide concentrations influence temperature, related climate parameters, carbon dioxide fertilization by plants, nitrogen absorption by plants, and other crop productivity factors. The Holocene approach is recognized for having thousands of years of favorable, stable temperatures that support both agriculture and human development. Based on historical proxy temperature data during the Holocene,
recent temperature measurements,
and future temperature projections,
we see that something very unusual is happening to temperatures compared to earlier times in our Earth's history. As of approximately the 1950s, we are unofficially leaving the stable Holocene and unofficially entering the Anthropocene, where human activities are having more of an influence on our climate systems than natural forces. There is only one scientifically supported explanation for these temperature increases. Changes in the carbon cycle are impacting crop production and yields.
Global average temperatures have risen by some 1 degree Celsius since pre-industrial times, and higher in many crop areas.
Based on the scientifically proven link between greenhouse gas emissions and temperature increases, with a lot of work and changes, we currently have an opportunity to limit global temperature increase to under 1.5 degrees.
The government-related links illustrated, along with the university and NASA links, allow one to explore, learn, and understand the science supporting greenhouse gas increases and future temperature increases.
Appropriate temperatures within crop-specific ranges are essential for producing high yields. Appropriate rainfall over the growing season is also extremely essential. As temperatures increase, evapotranspiration rates are higher, potentially creating water stress challenges for crops. Richard will next introduce climate parameters. Richard?
Later in this series we describe the direct climate parameters including temperatures, precipitation, and wind. Thermal units are commonly used in agriculture for crop development stages. They are calculated from maximum and minimum temperatures. Optimal maximum crop temperatures are based on historical observations. Changes in the direct climate parameters impact the indirect climate parameters including humidity, vapor pressure, dew point, evapotranspiration, and vapor pressure deficit. Each of the direct and indirect climate parameters influence crop production and yields. Crop models can simultaneously simulate several direct and indirect climate parameters for projecting future crop yields.
Linda will introduce soils and biodiversity. Linda?
Thanks, Brian. Productive soils are key to productive crop yields. Soil textures are based on the relative percentages of clay, sand, and silt, and indicate relative water holding capacity and other soil parameters. Multiple soil parameters are incorporated into crop modeling tools to better understand crop production. In addition to soil, other ecosystem services include water, microbial activity, nutrients, biodiversity, pollination, insects, genetics, and waste recycling. Appropriate water and nutrient supplies are critical for crop production. Ecoregions are based on major climatic areas where common flora, fauna, trees, vegetation, and insects are typically found. The habitats for the types that prefer milder climates are typically in the more southerly areas. Pollination services are important. Over 75% of the world's food crops rely on pollination, including specific types of grains, vegetables, fruits, and oil crops. Beneficial insects are important for crop production. Natural predators are important for pest control. An environment free of weeds, pathogens, pests, and pollutants is needed to achieve maximum crop yields.
The 7 land classes presented here are based on definitions. Prime agriculture land typically refers to the top 3 classes plus organic soils. There is a substantial amount of Class 1, 2, and 3 lands in southern locations and hardly any of Class 7. The area to the north having a similar color to 7 is not classified and not agricultural land.
There are a variety of land classes in the more eastern areas. The boreal shield is located in the northern areas, limiting the prime land classes and agriculture to the more southerly areas.
Preserving prime agricultural lands for food production is important for our future food security. Increasing temperatures impact ecosystems, biodiversity, pollination, phenology, pests, and disease. Increasing temperatures above crop-specific levels impact crop production, yields, profitability, and food security. Changing temperatures impact plant, soil, microorganisms, and soil microbe-to-microbe relationships. In addition, increasing carbon dioxide levels may impact the nutrition levels in food. Net emission reduction technologies, such as carbon dioxide removal and sequestration, are needed. Examples of extreme weather events that impact crop production and yields include heat waves, droughts, and floods. Extreme weather events damage crops, cause soil loss, and change soil moisture content. Extremely hot temperatures during the flowering phase negatively impacts crop yields.
Soil erosion and runoff of nutrients to water reservoirs increases with more extreme downpours, extensive droughts, and damagingly high winds. Increasing temperatures impact soil organisms and microbial networks. Increasing temperatures result in more soil organic carbon being released from soils. As our climates change, many of ecosystem services described above are changing. A loss of pollinators and a loss of insects in general has major consequences for entire ecosystems, including agroecosystems. Decline of specific monarch butterfly colonies are well documented, and many organizations provide services to counter declines. The timing of life cycle events, known as phenology, are changing. Crop production and yield depends on various ecosystem and biodiversity resources. Both pests and disease are expected to increase as temperatures warm. Worldwide, pests currently eat an alarming percentage of crops each year. In warmer temperatures, insect metabolism increases, their life cycles get faster, and they reproduce more quickly. Without changes, pests will be consuming yet more of our crops in the future.
Globally, urban sprawl continues to consume prime agriculture land.
The darker reddish circled area is very high-density urban area. The reddish area is increasingly urban with limited and decreasing agriculture. The amber area contains both urban and agricultural areas today.
There has been a significant increase in urban sprawl over recent years, as illustrated in the 1984 versus 2016 images. The greenish area in the center is protected natural lands, most of which are part of an escarpment and too hilly and rocky for urban uses. Climate change affects land use. Urban sprawl on prime lands is more than a waste of valuable resources. However, recent initiatives are helping to preserve remaining agricultural lands.
Nutrition is viewed from 3 perspectives. First, how climate change impacts resource sustainability, the effect of carbon dioxide concentrations on food nutrition, and 3, the impact of climate change on food security. Changing climates may impact our food imports, and we have food export obligations to meet. Globally and locally, the impacts of changing climates and increasing temperatures on various resources and crop production as illustrated above can affect one or more of the 4 dimensions of food security.
Reducing air pollution and greenhouse gases, plus mitigating climate change, can improve both human health and planetary health.
Climate and crop modeling tools can project future food production scenarios for local and international needs. One example is the coordinated global and regional assessments for climate change impacts on agriculture and food security.
Output from these models can provide input to integrated assessment models. One example is for projecting the social cost of carbon. It is the projected economic cost in today's dollars for each additional metric ton of carbon dioxide equivalent emitted to the atmosphere. Based on full life cycle analysis, calculations estimate how much gross domestic product is cut by various climate impacts. Examples of climate impact costs include extreme weather events, changes to agricultural productivity, crop losses, and health costs. Current estimates are that it is an alarmingly high future cost that makes any price on carbon today look extremely small. Corporations need to report on and meet various sustainability goals as mandatory requirements for financing and being recommended as climate-safe investments by investment advisors. It is very important to project future sustainable food production scenarios using newer modeling tools. Recent graduates are highly suited to participate in the modeling processes for climate and sustainable food resources.
In this video, we have summarized several natural resources that are important for crop production, along with respective impacts on these resources as a result of climate change.
In the next climate and sustainable food resources video, we will introduce 4 additional resources that help to increase productivity, yields, mitigate the impacts of climate change, and ensure sustainable agri-food systems. New technologies, sustainability, modeling including crop modeling, and knowledge resources.
In upcoming videos in this series, we introduce crop growing areas for several crops and livestock, such as corn and potato growing areas. We also introduce the green belt, the clay belt, and indigenous areas. We ask where else could we grow these crops as our climates change, and what crops will we be growing? Linda will now test our knowledge of the key concepts.
What are the agricultural sustainability areas highlighted in this video? Mitigating climate change, protecting prime agricultural lands, open data and modeling tools.
This video series would not be possible without all of the amazing tools, open source tools, and open data. Please pause the video to review the various tool developers, organizations, and sources of knowledge that help to make this video possible. Thanks. Thanks for watching. I hope that you have learned from this video. You may subscribe. See you in the next video.